last time we talked about solving ordinary differential equations with series. And I want to sort of recap because I don't know if we fully stated the process. So I want to make sure we understand the process. So the idea here is we say, well, let's assume the answer is a series. So to be a series is just another way of saying it's an infinite polynomial. So if you don't like the word series, just remember in the back of your head, it's a really big polynomial. So, all right. So we say, all right, our answer looks like a series. We just have to say, what are the c sub k? And that's where our energy goes to, is how do you solve for the c sub k? Well, we have a differential equation, and so we say, all right, what do we do? Well, we say our old mindset is, if we know what our solution is, we plug it in. So that's what we're going to do. We're going to plug this in, and we're going to say, all right, what does this tell us about what our c sub k have to be? So, all right, we build up our collection of differentials, y prime, y double prime, whatever we need. We substitute in, and we combine all the resulting series into one sum. Now, that sounds really innocent, this part. This is where all the work is, this one sentence, is you want to make sure you can do that. So it's what we talked about last time. There's a fairly straightforward process. The first thing is you really want all the powers to agree, and you do this by doing your shifts, the substitutions. The second thing is you say, look, I want all starts to agree, and you say, all right, well, that we can pull off by just pulling off the terms if we need to. And then we can have all our starts at the same point. And then once that's all good, we can combine everything into one series with a few terms at the start pulled off that follow a slightly different pattern. And now, the last thing is say, all right, now that everything's combined together, and remember, what's the theme here? When we talk about combining all resulting series into one series, the real theme is we're grouping all coefficients of the same power. So it's like I want all the things that are the coefficients of x cubed together, all the coefficients of x to the 17 together, and so forth and so on. So when we talk about combining, that's what we're doing. It's like we're making sure all our coefficients line up. And then we compare coefficients because we have two sides of an equation. A differential equation says there's a left side and there's a right side. We say, okay, take the right-hand side, coefficient of x to the k, compared to the left-hand side, coefficient of x to the k, and say, does it work? Well, it has to, right? And that gives us relationships, and that helps us solve for our coefficients. Now, there's a phrase here, which we didn't use last time, which is a recurrence relationship. And what that means, a recurrence relationship just says, I can connect my current coefficient back to previous coefficients. And the idea is you start at the beginning of your series. So you start with your constant term, then you start with your coefficient of x term, and you build up. And so that at any given point, the current coefficient you have to compute can be computed by using earlier coefficients. So that's the idea. We basically got most of the way through an example last time. With good luck, we'll get through 2 examples today. There's a couple of things I want to talk about. This is the how. This is the how. And at some point you're like, okay, I can get the how. It's not such a crazy idea. I substitute in, I group coefficients, I line things up, and I solve for these coefficients. But perhaps there's another question we should talk about, which is the why. Why are we doing it this way? What's the point? Because I think it's helpful to understand why we do things, not just how we do things. So here's sort of the ideal. It's like we start with a differential equation, and so here we have our differential equation, and the ideal scenario would be to do what? Well, solution. That's the ideal. That's what we want. Now there's a couple challenges. This is hard. And in some cases, our solution is just not even representable by functions that we have. The solution is a function that we don't know of. It doesn't have any nice representation using things like the exponential function, trig functions, polynomials, or any combination thereof. Most functions are unpleasant in some sense in that regard. So this is ideal, but the problem is it's hard, if even possible. So we say, okay, all right. So what we do is we say, all right, well, what can we compromise? Can we find sort of the right setting? And so we visualize ourselves as engineers. So we're visualizing ourselves as engineers. All right, I see myself not eating ramen every day. Okay, I see myself affording a haircut more than once every other year. Wait, I'm almost there. Yes, okay, here we go. As an engineer, I see myself saying, I don't need to have it exactly. I just need to know it approximately. See, that's the great thing about engineers. They say, look, close enough is good enough. So they say, okay, you know, what we can do is we can approximate. That's how most differential equations are done. So we get an approximate solution, right? So this is not exactly the solution, but it's pretty close to it. And say, well, all right. So now the question is, well, how do we get an approximation to our solution? Well, there's a couple different ways. Now, a way that is very frequently done is through the use of computational tools, and they call this numerical methods. And the computers will grind away and get rough approximations. And that's something we haven't talked about in this class, but if you want to learn more, we're happy to direct you to other classes where you can learn about it. But another idea is to say, you know, we can say the following. If we have a solution, see this y equals the sum, k equals 0 to infinity, of ck x to k. This is a solution, and I'm going to be a little careful here, locally. I'll come back to what I mean by that. So the series is a solution. But now, that involves a lot of terms. You have to go all the way up to infinity. So what can we do, though? Yeah, we cannot go to infinity. We can just say, look, I'll just compute the first 20 terms, and I'll call it a day. And so another way to get an approximation is to say, oh, I can just do the sum from 0 up to some stopping point, ck x to k. And what I get is a polynomial. It's not the full solution, but locally it's a pretty good approximation. And that's good enough for us. So that's the idea. Why do we care about series solutions? It's a great way to get approximations. That's why we care about it. So, all right. Well, one other question, of course, to ask is, what can we say about our solution? Because there's this word locally I brought up. Because sometimes when you have series, there's a question of, does it make sense? Because I can write down series that, okay, they're perfectly valid as a mathematical expression, but totally useless because they don't have any meaning. And so what do we want? Well, we want the sum to actually go to a value. In other words, we want it to converge. So there's something called the radius of convergence. And the idea of this is saying, you know, how far does this series converge? In other words, where is this good? And we spent a lot of time in Calc 2, I think maybe a week, maybe even more, talking about the radius of convergence. And I don't want you to stress about this. That's not our goal here. Our goal, we're going to talk a little bit about it, but just know that there's this notion of convergence. And this is a fact from Calc 2 that says, actually, you can compute the radius of convergence by seeing how big is the ratio of two consecutive coefficients. But we're going to look at it in a different way next time. So when we come back on Friday's class, we're going to look at this and say, and here's a different way to think about how do you figure out radius of convergence. And we'll see, oh, there's actually a really simple way to say, at least it's good for this far. All right. Well, that's philosophy. Any questions before we get into practice? All right. Well, in that case, we want to practice solving differential equations with power series. So we're going to have a very simple differential equation to start with. Y prime equals 3y. And y of 0 equals 1. And we want to solve this by two different methods. Method 1, a separable ODE. Method 2, use of power series. And then there's a question. Are these the same? E to the 3x. Did everybody get the same answer? Do you remember how to do this? Okay, so as a reminder, separable says separate y prime over y equals 3. We've separated. Or another way to say this, because you can think of y prime as dy over dx, dy over y equals 3 dx. And then you integrate. Integral dy over y, natural log y equals 3x plus a constant. Put both sides into the exponential function. Y equals e to the 3x, and then the constant comes down. You say, oh yeah, that's right, this is the exponential model. How do you solve for the constant? Plug in 0. And y of 0 equals c, which equals 1. And so you get y equals e to the 3x. Good. All right. Well, that's not so bad. All right, so how do you begin this? What's your first step? If we think we should use a power series, what should we do? Yeah, we should set y as a power series, right? Because if you think it's a series solution, you say, let's start with the series. We need y prime, so we say, okay, let's find y prime. Now, they take the derivative term by term, so the k comes down, ckx to k minus 1, and we'll do a quick shift here. So it's the sum, 0 to infinity, L plus 1, CL plus 1, x to the L. So we have series for y and y prime. Then what happens? Yeah, we substitute. We plug stuff in. Where we see the y prime, we put y prime. Where we see the 3y, well, we take this and multiply it by 3. That leads to this. Our y prime and our 3y. So I moved the 3 inside, and then I took the time to say, oh, let me make this all in terms of L. So life makes sense. All right. So far, how are we doing? Did you get there? What comes next? Well, we can write it as one sum, but we can also do what? We have polynomial equals polynomial, so what has to be true? Coefficient has to match coefficient. So, that tells us that L plus 1, C sub L plus 1 has to equal 3 C sub L. Or I can say C sub L plus 1 is 3 over L plus 1 CL. So in other words, if I want one coefficient, I can get it from the previous coefficient. Now, of course, you might say, but how do we get any coefficient? Is there any coefficient we get for free? C0 is a freebie. Why is C0 a freebie? It's given. It doesn't say C0, but y of 0 is just another way of saying C sub 0. Okay, so we know what C sub 0 is. If I have C sub 0, can I find C sub 1? How? Plug it into here. If I have C sub 1, can I find C sub 2? How? plug it into here. And it keeps going. Okay, so we have our y0 is C0, which is 1. C1, well, according to our rule, so if I want C1, I put in L equals 0. So that's 3 over 1, C0. But C0 is 1, so that's 3 over 1. C2, well, that would be L equals 1. So that gives us 3 over 2 C1. But I know what C1 is, so I can replace C1 by 3 over 1. So 3 over 2 times 3 over 1. Now C3, that's L equals 2. 3 over 3, C2. So 3 over 3, put in what C2 is. 3 over 2, 3 over 1. Yes? And you keep that going. So C4, we start seeing the sort of the pattern. It's 3 over 4 times 3 over 3 times 3 over 2 times 3 over 1. C5 is 3 over 5 times 3 over 4 times 3 over 3 times 3 over 2 times 3 over 1. And all the way down. And they say, well, look, in our numerators, we get bunches of 3s. In our denominators, we get things like 4 times 3 times 2 times 1. Or 5 times 4 times 3 times 2 times 1. I'm like, we know these things. Upstairs, it's 3 to a power. We just figure out, well, what's the right number of 3s? It turns out, if I'm like at C5, I have 5 3s upstairs. So in general, if I'm at CK, I should have 3 to the k. And downstairs is a factorial. So C sub k is 3 to the k over k factorial. Which means there's our series. So our series solution is the sum, k equals 0 to infinity, 3 to the k over k factorial, x to the k. Now I know you're suspicious. You're like, Steve, you have a little piece that you've hidden here. Okay, so that's not more answer. It's just a comment. So when you're looking for a pattern, and so this applies if you're saying, oh, I need to find the pattern of coefficients, be careful about simplification. Simplification can become obfuscation. And now you're like, wow, that sounds like an English word. One of those big $10 words. It basically says, if you simplify, you might miss what the pattern is doing. So what do I mean by that? Notice 3 over 3. Normally, what would you do with 3 over 3? Yeah, it becomes a 1, and you would just not even bother to write 3 over 3. But if you did that, then you'd have, here you'd see, oh, I have 3 3s upstairs, and I have 4 times 2 times 1. And it's harder to see that, oh, wait, here I see, oh, bunches of 3s factorial. Here, I don't see that. And so if you are looking for patterns, then you want to be careful to not simplify, because simplifying can obscure what the pattern is. All right, but the moral is, here's our series solution. I see a question.
So in the y prime, when you first made the series in y prime, what was k equal to 1 instead of 0? Was it because of the initial condition?
Well, so initially the sum was from 0 to infinity. So the question is, why can we change it to 1? Well, the answer is, what happens when you plug in k equals 0 into this expression? Well, you have that 0. It's really hard to recover from that. And so it's like, well, let's just throw that one out. So oftentimes it can be very convenient to, when you take these derivatives, to say, oh, I can ignore the first 1 term in the first derivative, the first 2 terms in the second derivative, and so forth. Okay, so let's transfer this. So the use of power series says, aha, it should be the sum from 0 to infinity of 3 to the k over k factorial x to the k. All right, so that's part 2. And now there's the last part of this. Are these solutions the same? Now, I'm not going to ask you to spend 5 minutes, but I hope you want to spend like 10 seconds and say, are these the same? So, okay. Ba 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 ba. Ba 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 bum ba 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 bum 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 ba bum 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 bum. Okay, all right. Now that you've had a chance to think about it, are these the same or are they different? they're the same. How can we know that these are the same? Formula sheet. I like that answer. All right. So on the formula sheet, it says something along the lines of the following. E to the z is the sum k equals 0 to infinity z to the k over k factorial. Now, I like to think of it in the following way. E to something is the sum k equals 0 to infinity of something to the k over k factorial. So I have a box here. The box just represents I can put in whatever I want. And then the question becomes, what's in the box? What's in the box? Okay, so what can we do? Well, let's start with, doesn't matter which one we start with, let's start with y equals e to the 3x. So in our case, what's the box? 3x. So this is the sum, k equals 0 to infinity of 3x to the k over k factorial. Well, but 3x to the k, how can you rewrite that? 3 to the k, x to the k. And so you end up with that. So our separable solution, and here's our series solution. And they're the same. Now you might say, well, Steve, there's a technical thing, right? When is this relationship true? Always. So yeah, so life is good. Life is good. All right, so yeah, they're the same. So look, now we see, aha, we could have solved this by separable, but now we can solve it by power series. We'll probably keep solving it by separable in this case. You know, why use a longer process when a simpler process works? Okay, any questions? Good. Then we're ready to move on to the second problem for today. Let's solve x plus 4y prime plus y equals 0 with y of 0 equals 1 by use of a power series. And determine the radius of convergence of the answer. Ooh, cool, radius of convergence. We'll get to that. And compare the answer to what we can find by other methods. Oh, man, there's a lot going on here, a lot to unpack. All right, but we'll start by the first thing it tells us, which is to solve this by use of a power series. So there's our differential equation. So how do we start by solving something by a power series? Yeah, we say, look, if it's a power series, so y is this 0 to infinity of c sub k x to the k. This y of 0 equals 1, how does that translate for us? C0 equals 1. Okay, so that's something we can translate. And then, of course, we have to go through. We'll make some notes here. Y prime is the sum k c sub k x to the k minus 1, which we can start from 1 to infinity. Okay, so we begin our journey. We have x plus 4 times our y prime, sum k equals 1 to infinity, of k ck x to the k minus 1, and then plus our y, sum k equals 0 to infinity, ck x to the k, and that equals 0. What do we do? If it helps, I'll casually point to something. It says, Yeah, we should distribute. Okay. So this is the same as x sum 1 to infinity k ck x to the k minus 1 plus 4 sum k equals 1 to infinity k ck x to the k minus 1 plus the sum k equals 0 to infinity ck x to the k. All right. Well, what can we do with this x? We can move it in. And this 4, we can move it in. So, this is the sum, k equals 1 to infinity of k ck x to the k, plus the sum 1 to infinity of 4k ck x to the k minus 1, plus the sum 0 to infinity of ck x to the k. And we set that equal to 0. All right, are we ready to mush these all into one sum? No. What's the problem? Powers don't line up. It's also true that stars don't line up, but powers come first. Powers are the most important thing because we are working towards grouping the coefficients. So we want to make sure the powers align. All right, so we'll fix our powers. So we go through and say, look, I like this one, so I'm just going to change my notation. And I like the last one, so I'm just going to change my notation. In the middle, what do we do? So in particular, what will L be? K minus 1. Or we could say K is L plus 1. So we go through the first one, nothing changes here. 1 to infinity, L c sub L x to the L. And we'll go ahead and do the last one, because that's, again, all we're changing is names. K's become L's. And 0 stays at 0. Now the fun one, the middle one. It's our sum. Where do we start this sum? At 0, right? Because K was starting at 1, and 1 minus 1 is 0. Where do we go to? We still go to infinity. The K becomes L plus 1. The C sub K, CL plus 1. And x to the k minus 1 becomes x to the L. All right, now are we ready to mush things together? No, not yet. What's the problem? Other than I forgot to make the first one an L. Shoop, there we go. Now, what's our problem? Yeah, the stars don't line up. Okay, so what do we need to do? We need to pull off, add a term. Oh, my dear friend, that's a dangerous thing. Oh, but actually it could work here. Should we do it? You want to do it? Okay, we can do it. We'll do it. We could pull things off, but we have had a suggestion. Why pull things off when we can push things in? What happens at L equals 0? If we started at 0 instead of 1, what would happen? So what's the difference? Yeah, so just do that. All right, cool. A fun suggestion. Okay, that sometimes works. Sometimes doesn't. Just a word of warning. But this time it works. Wow, the stars have aligned. Okay, now are we ready to mush things together? Yes, okay, all right. Ah, the fun begins. Tra-la-la-la-la, la-la-la-la-la-la, tra-la-la-la-la. Okay, what do we see? We have a 4L plus 1, CL plus 1 from that one. Then we have an L C sub L and a 1 C sub L, which is an L plus 1 C sub L, times x to the L. And that equals 0. Yes? Yes. Good. Okay. We are building some consensus here. Now what happens? Well, what's true about this coefficient? Has to equal 0. Okay. So, for L plus 1, C L plus 1, plus L plus 1, C sub L equals 0. And this is going to start being true starting at 0. And this is for L greater than or equal to 0. Well, can we simplify this? Sure. What are some things we can do to help simplify this? Yeah, we can just knock out the L plus 1s. We don't need them. Okay, they're gone. We don't need them. And then we could say, okay, well, C sub L plus 1 is equal to, we move it across, divide, minus 1/4 C sub L. Oh, somebody worried about I might have divided by 0? No. Now you're making me paranoid. Like, what? Steve, could you have divided by 0? Well, when would L plus 1 equal 0? -1. Do we need to worry about L equals -1? No, because we only care about L bigger than or equal to 0. So, there's a fun, well, I don't know if it's a fun story. There's a story I can say. I'll probably save it for another day. All right. We're going to put some new white space here. We know C0 equals 1. What can we say about C1? -1/4 times C0, well, which is -1/4. How about C2? -1/4 times C1, so that's -1/4 times -1/4. How about C3? -1/4 times C2, right? We're just using the same recurrence. So here is the L equals 0, L equals 1, L equals 2. Well, so that's -1/4 times -1/4 times -1/4. Do we spot a pattern yet? Okay, so what does that say about our C sub k? -1/4 to the k power. All right, cool. So now we say that's our pattern. Our solution is y is the sum from k equals 0 to infinity of our -1/4 to the k, x to the k. Okay, so this is our solution by a power series. Now we can go to our next question. Radius of convergence. All right, and I know people are like, no, Steve, I'm still recovering from Calc 2. Okay, but we'll just use our fact here. So our radius of convergence, we'll put it down here, rho. This is our limit as n goes to infinity of the absolute value of Cn over Cn plus 1. Okay, but we know what these look like. Cn is -1/4 to the n. And downstairs is -1/4 to the n plus 1. Well, does that expression simplify? It's like 1 over -1/4, also known as -4 when you take the absolute value. 4. So this is limit as n goes to infinity of 4. What's that limit? 4. So that's the radius of convergence. Okay, so that's when we have the same answer. Well, that's when this answer makes sense. Okay, so good. So now we've found our solution. We know when it works. Compare the answer to what you can find by other methods. Okay, so let's do another method. What other method might we be able to implement here? X plus 4y prime plus y equals 0. Anything jump out and say, ah, I see a method that could work. Integrating factor. We could do that. Or we could do the same thing we did on the last problem. This is separable again. Because this is 0, we don't need to do an integrating factor. So x plus 4 dy dx equals minus y, or dy over y is equal to minus 1 over x plus 4 dx. Integrate, integrate. What does that tell us? Natural log y equals minus natural log of x plus 4 plus c. Oops. It's an arrow, not an equals. What does this minus do? Yeah, it can go inside the log as an exponent. So this becomes natural log of 1 over x plus 4 plus c. Well, and now, free it, y equals some constant c over x plus 4. But, what else do we know? Y of 0 equals 1, right? So, y of 0 equals 1. If we plug in 0 to here, what do we get? C over 4. So what's our answer for C? C should be 4. So we come to the conclusion that y should be 4 over x plus 4. Okay, so here's our answer by other methods. But we want to compare. So we have two different answers right now. So one answer is this sum, 0 to infinity, of minus 1/4 to the k, x to the k. And another answer is 4 over x plus 4. And the question is, are these the same? Probably. Well, is there anything that can help us? A formula sheet might help us. So the sum from 0 to infinity of something to the k power is equal to 1 over 1 minus our something. Okay, so notice that this is the sum, k equals 0 to infinity, of minus x over 4 to the k power. So according to our rule here, this is 1 over 1 minus x over 4. What does 1 over 1 minus x over 4 become? Because you can, 2 minuses, 1 plus, multiply top and bottom by 4, and you get 4 over x plus 4. So, I still have a little bit of time left. I'm going to ask you a question. I'm going to ask you two questions. Are these the same answer? And why not? So, are these the same answer? No. Very good. Why not? Because I see equalities here. I feel like you're lying to me, Steve. Radius of convergence is the answer. See, this equality doesn't hold for all x. Now, when is this solution valid? Ooh, be careful. everywhere above -4. We can't push below the asymptote. So don't worry, that just means I'm out of time. So we can't go below the asymptote. So we're only valid here above -4. But when is this solution valid? From -4 to +4. So this solution only converges radius of 4. So this is like they overlap, they agree for a while, but one will extend further and one will stop working. So that's why you have to be careful. All right, that's it. Thank you, and have a good day.